Did y'all mess with the lights yesterday? The lights are like on, but they're not all the way on. You're just gonna be in the dark for a second. Well, I'm trying to reset it. Don't you know that we were here to solve any problems and shut it off and you want it back on again? No. I think it's just probably good. Oh, okay.
Maybe just for hire.
That's normal. That's normal.
I think so too. It does for me.
Well, my way worked. I'm not sure your way would. Okay, so I think we're set. So yeah, I guess whenever you're ready.
Okay. Okay, let's get started with neutrino stuff. So yesterday we wrapped up what I wanted to talk about for neutrino oscillations. But before I forget, I wrote down oscillation probability for long baseline appearance channel. And I said that it has three terms. And we can look at one of the terms that has matter effect, and you can see how to use that to measure mass hierarchy. And then I also write down a term that has delta CP in there, with a term looking like this. And some of you correctly pointed out that from what I wrote prior to this term, it looks like this does not go to 0 when L goes to 0, which would be a big problem. And turns out that in my notes, I had ... which means I skipped some of the terms. So there's a bunch of sine angles and cosine or sine angles. And it includes terms like this, delta 3,1, delta 2,1, etc. And in the delta definition, there's multiplying L. So there's explicit L multiplied in the expression. And similarly for term 1, 2, 3, you can check the expression, which I took from Dune CDR, that all the terms explicitly go to 0 when there's no distance. So always good. There's no oscillation when there's no distance for the neutrino to have oscillated yet. Okay. So yesterday, the second part, I started to introducing the so-called neutrino nucleus scattering cross-section problem. So let's continue on that. So hopefully I explained that in order for the cross-section calculation to be useful, you really should look at what part of the cross-section the experiments cannot measure. And that's the part that you really have to get it correctly. And the takeaway is that the cross-section we need is neutrino interaction at certain energy, because everything has energy dependence. And you really want to check how many neutrons are produced and what's their spectrum, because this is the thing that experiments really cannot measure. But at the same time, you also want to see, how much energy goes to proton and what are the proton spectrum, and how much energy goes to pion, and etc. So all the exclusive information of a neutrino nucleus interaction. Okay, so next, I think I want to go over just schematically, how do people compute this range? Okay, so let's say, again, the energy goes from, 0.5 to 5 GeV. So let's start at the highest energy. So I'm just going to use E nu, but the thing that's more important is, energy momentum transfer. But at high energy, let's say 4 or 5 GeV or so, you're sort of okay, or mostly, to use the DS formalism. So where you can treat your hadronic degrees of freedom to be quarks, like the following. Oh, I forgot to say. The first step to calculate this, how a neutrino would interact with argon, carbon, or oxygen, is to do the easier step. So step 1. This is mu. I can't. So this is the weak part that stays the same. Step 1 is let's compute a much simpler process. Neutrino interact with proton or neutron. A single nucleon free at rest. So ignore the nucleus part. Okay, so at the highest energy, it's like sort of, you can use DS. And at the lowest energy, it's also sort of okay. So again, the top is always neutrino mu, implying that I'm using nu mu here. And then at the lowest energy, let's say below 1 GeV or so, it's reasonably to assume that the hadronic degrees of freedom is just a proton-neutron. And this is so-called quasi-elastic scattering. So let me raise it up a little bit. And the highest one, the parton one, is DS. And in the middle, if you ever look at these spectrum, when energy goes low for our usual energy range, or energy goes high if you're more familiar with the nuclear sort of degrees of freedom, in the intermediate range, what you would see is baryonic resonances. So the simplest way to think about it, the way I think about it is, so low energy, you have neutron goes to a proton. If there's more energy going in, you can just excite this proton. And like delta is the lowest excited states for a proton. But of course, there's many baryonic resonances, so there can be a bunch of possibilities. So this is called resonance production. Okay. So again, the idea is pretty simple. We are crossing a range of, nucleon baryonic resonances and partons in terms of hadronic degrees of freedom. And we don't have a theory that deals with everything in one theory, right? So people chop up the phase space, and in part of the phase space, it's kind of okay using one of the scenarios. And in the end, you just add them up in terms of total cross-section. So conceptually, that's how the treatment is done currently. Okay, and this is the first step. So again, right now, we're just dealing with neutrino interacting proton or neutron. There's no nucleus yet. And then the one way to think about it is after that's done, so you have to put everything, whatever your interaction channel is above any of the three, you have to put it in the nucleus. So for instance, let's look at the first diagram where initially I have a proton, and initially I have a neutron, afterwards I have a proton. So nuclear effect come in a few different places. For instance, first is this neutron is not free at rest, right? It is inside the nucleus, which means it has some position distribution, and it has some momentum distribution, also it's bound. So then you have to, again, the simplest way to think about it, you have to modify something about the neutron to put it in the nucleus. Let's say you put it in an argon. So that's one of the effect. Another effect is similarly on the final proton. Suppose this neutron is here, you'll interact and produce a proton. Now this proton is, I guess I want to draw a similar location here. This proton is here in the nucleus. It's not outside yet, right? So it still has to propagate out. And as it propagates out, it's going to run into other protons and neutrons in the nucleus. So for instance, this proton could further run into a neutron here. And let's just say it's an elastic scattering. But what happens is the energy of the proton will now get transferred into some energy of the proton and some energy of the neutron. Why does this matter? Remember, the thing that we're trying to predict is the fully differential cross-section for all the hadrons. So these would change how the energy distributed. That's why you need to compute it. And some other effect, for instance, it's a pretty good approximation that you're just interacting with a single nucleon or parton at high energy range. But sometimes there are tightly bound pairs, for instance, rather than interacting with a single neutron. This neutron is really bound with a proton pair. So you can now treat as just isolated one nucleon here. So a bunch of nuclear effects like this, which is related, but which is conceptually easier to think it's kind of like a separate problem from the primary vertex, which this problem is really just because of phase space. We're doing calculation at q squared of 1 GeV squared. So, okay, any questions about that? Yeah.
Could you remind me the energies, like what is high energy, what is low energies, and what is intermediate?
Right. So it's not exactly because it's not exact because it's more energy momentum transfer, and also even how to divide this. It's not like there's a well appreciated, agreed on recipe. But roughly speaking, this channel dominates at energy below 1 GeV, roughly. This is more like I don't know, 3 GeV and above. At least how we are dividing the phase space. This is kind of like 1 to 2, 3-ish GeV in the middle, roughly. But again, one of the difficulties in combining things is really there's no guideline to tell you that, oh, in certain part of phase space you have to use this. In certain part of phase space you have to use this. In certain part of phase space you have to use this. One of the difficulties is we don't actually know when do things stop being resonance and become partons. Or I guess this one's sort of well separate, but like how do we separate these channels in phase space? That is extremely open question. So this is more how we are currently cutting things. Okay, any other questions? Very quiet. Okay, I think I want to make a short comment. How would we, okay, so then let's look at a particular channel. And I can just describe why this is difficult to compute each individual channel. So this is just a simple example. So let's look at quasi-elastic scattering. Where again, it's relatively clean because the hadronic degrees of freedom just protons and neutrons. So if you think about, let's say instead of considering a W exchange, let's consider something you've probably seen in textbook, which is just a gamma exchange. Let's now instead consider gamma go to proton and proton. So how would you try to compute this? So this, if you remember, looks very similar to a diagram you had computed in Peskin, which is gamma go to EE. Of course, the one in Peskin has a loop, but let's ignore that. So the way to compute this is, I know I have a spinner. going out. I know I have a spinner. I have a spinner coming in, spinner going out with a current, right? And it's going to look something like U bar something U. And the argument is by using, Lorentz structure and etc., you can figure out the Lorentz structure of the current. And for instance, for QED, it has first gamma mu term. And it also has something that looks like 2mi sigma mu nu QU F2. Like the following. So the idea is you can figure out the Lorentz structure of the current, and with other unknowns, you can parameterize something called form factors. Again, this is something that you had done in QED when you figure out how to compute this vertex. Now, the beauty in QED, of course, once you can write down things within the form factors, and you're able to compute form factors precisely because you know how to compute a QED loop. Now, the difference here is instead of having electrons, we have protons on the leg. So which means that I do not have a particular way to compute what are the form factors. So another way to think about it, if you don't see form factor often, it's kind of like PDF. It's a thing that we figure out to parameterize non-perturbative effects. So the other things we know how to compute, and we don't know what are the form factors. So because it has non-perturbative QCD in there, so there's essentially two classes methods to compute it. First, there's lattice QCD. And lattice QCD are indeed good method to compute these form factors. And there, the difficulty is just there's like something like under order of 100 form factors that need to be computed. And lattice QCD calculations are expensive, are difficult. It takes a while to figure out what are the correct systematics. And there's a lot of effort right now ongoing trying to compute these things. It just progress has been slow from a user perspective. And another way to figure out what are the form factors is kind of like PDF. We fit to data. We figure out some way that they should look, and then we try to fit as much, we try to utilize as much data as possible, trying to figure out what they are. And which is right now practically how most of these form factors we use are from. And there, the difficulty is, again, we have so many form factors because there are so many baryonic resonance states, so on the order of 100. And this is a region we have a lot of data, but just not enough. Especially, so these couplings are vector couplings because I'm writing down QED form factors. Of course, when we are actually exchanging a W, so there will be axial form factors where we need neutrino scattering data. And we obviously have not scattered neutrino at each baryonic resonances and took measurements. So there just we have very limited data. And so that's sort of like, hopefully you can get a sense of why this calculation at individual channel is difficult. And you have to combine them, you have to treat nuclear effects, and et cetera. Okay. Any questions? Yeah.
You said there are 104 factors. Are there degeneracies?
Great question. So there are not sure degeneracies is a good word, but there are issues in terms of mixing. You don't know which one is which. So one of the things you can, I can explain is the following. So let's say we have different baryonic resonances. If they're all well separated like this in invariant mass or something, so then once you take data here, you know you're measuring this resonance. When you take data here, you know you're measuring this. So there's no mix. So then that's not bad, right? The issue with these resonances is that they're very close and they're also broad. So rather than this picture, which would make our life a little bit easier, we have this picture. You got the idea, right? So then even if I take data, which we have been doing, like once you're sitting here, which one are you, and I'm only overlapping one state, like 2 states, but imagine they're all overlapping. So which one is it? So that's why right now there's already a lot of data available, but there's still actively ongoing work, people trying to figure out how to get this better. And the fact that they're being broad, it is a big problem. Okay, any other questions? Yeah.
What's setting the width of that resonance?
Well, these resonances are not stable, right? They all have basically just decay width. Sorry. What sets the width of the resonance? These are not stable resonances. Like delta has a very, I don't remember the width of the delta, but these are all pretty short-lived things. Okay, any other questions? Okay, I don't know if it's because of the topic, but I feel like the mood in the room is a little different. Or the fact that it's early, so I don't know which one it is.
Certainly, when I have taught, teaching at 9 a.m. is dramatically different from later.
Okay, to make myself feel better, I'm gonna say that's the reason. Okay, so let me wrap up the, I guess, unless you want to hear more details, so I'm gonna wrap up the cross-section part. So the takeaway is the following. We need cross-section because that is the main detection channel happening on all of these experiments. So regardless of whether you need a total cross-section or differential cross-section, it's easy to imagine that this is something that these experiments need as a theory input. And I think because it's called neutrino nucleus scattering problem, I think a lot of people have this impression that the only problem we have with this difficulty because we're scattering things on argon, which I hope I explained that that's not the case. Even if we have a proton tank, then we still would have more than half the problem. The problem is really the fact that, first, we're at least dealing with hadrons, so we don't have a tank of electrons as the target. And we're operating in something like a q-square of 1 GeV square. There's just no great way to compute stuff. And so that's sort of like, if you hear some of the phrase, so that's what each part of the calculations mean. And hopefully I explained why each part of the calculations is difficult. And then there's also additional difficulty in terms of combining things and stuff like that. So this whole problem is just open. And we certainly need any form factors lattice QCD folks can give us. But these calculations are hard. It takes time. And we certainly need as much scattering data as we have. So right now, there's already a lot of electron scattering on nucleus, which is helpful. And we need neutrino nucleus, neutrino scattering data, which in the future, near detector will provide. And even right now, we have some scattering data. And that will all help us improve the modeling. But this is not an issue, because this is not an issue that someone will come up with a perfect EFT that just can compute everything from first principle. I don't see that happening, at least not in the next 10 years. And so, at the end of the oscillation discussion, I said, oh, here are 2 open questions you can write a paper on. And I hope it's clear that for this problem, any question you can think of, you can write a paper on it. And it's not because people have been lazy. I mean, there has been a lot of effort going into compute this, but it's just, it's fundamentally open question. There are many different ways to compute these things, and we just basically need all the effort we have. So if you are, if any of the calculus drawing looks interesting to you, think about how to compute it. Yeah?
Can you just comment on the event generator approach to solve this problem?
Sorry, could you repeat it?
Can you comment on the event generator, neutrino event generator approach to solve this problem?
Can I comment on event generator approach to solve the problem?
To simulate this FSI's modeling.
So I'm not sure I understand the question, because the way so I'm just commenting on what I think about event generator. So because these calculations are, you see this multiple, let's say 5 separate models that needs to be mashed together to do a full calculation for experiment. So practically all of these things are implemented in event generators. So kind of like Pythia. But for the neutrino ones, the common ones you might hear about is something like Gini, Gibu, Neuro, etc. And So they certainly play an important role. And I think on the event generator side, there has also been a lot of progress in terms of having more event generators. How do they compare to each other results? And modularize event generators so that it's easy to swap out models. But I think right now, the event generator for neutrinos is not as, say, mature as the event generators in the collider world. Yeah?
How much precision do you need in those form factors?
Great question. So a question is, how much precision do I need for the form factors? So that's my next comment. So you might be looking at this, you're thinking, well, I'm not really an EFT person, so obviously, this problem has nothing to do with me. I would say that's quite the contrary. So on the phenomenological side, for instance, there are also pretty much all open questions. So one question, giant question that's not being answered is, how precise do we actually need these calculations? So to answer your question, how precisely do I need to know each individual form factors? I don't know, and we don't know the answer. Because it's, for instance, some of the very easy phenomenological analysis. Let's say, if you take, okay, so because we don't have first principle calculation, we also don't have first principle estimate of the errors, theory errors. But let's say the simplest way for a theorist to estimate theory error is to take two generators, take their difference as a theory error, and that's fine. Let's just take that as our current uncertainty on cross-section. How much would that actually impact CP measurements, let's say? That is an open question. So the first paper on this, I think, came out when I was in grad school. And right now, many years later, I'm still writing a paper on how to do that. So on the phenomenological side, because there are just many factors at play. And so people constantly argue about what other effect that you have to take into account and which are the effect you don't. And right. So on just a practical perspective, most of the questions, I would say we have concretely answered very few questions. Okay, yeah.
I was just wondering, these form factors are universal there, in the sense like, if you have an excited nucleus, for instance, or like just different configurations of the electron shells, like would they change drastically, or do I need to compute them for like every excited version of the same nucleus?
Right, so these form factors, so I think the question is, I interpret the question as, are the form factors the same for different resonance states? Yes, because they have their own, quantum numbers, essentially. Right. Okay, any other questions on this? Okay, if no, then I'm gonna move on to my third topic. Probing BSM and astrophysics in neutrino experiment. So the premise is simple. So we have to talk about how to probe the, let's say, standard neutrino oscillation physics using these experiments, current generation, next generation experiments. And then the cross-section is one big, let's say, footnote to keep in mind that in order for these experiments to reach the expected precision, there's this urgent need for better theoretical calculations of cross-section. Okay, but now let's change our premise to say, suppose that all can be done. What other physics can we do with these experiments? So I wrote a couple examples. I'm obviously not doing well on time. So I have 30 minutes left. Why don't we take a vote?
No, you have 45 minutes left.
Great. That may help. Okay, that would help greatly. So let's continue on what I had planned to talk about. So I organized obviously there's a whole zoo of BSM or astrophysics cases that we can probe in these experiments. And it's by no means an overview. So I thought that I would organize the kind of probe by really experiment. So the first one is BSM in oscillation. Okay, meaning that we are still measuring the things that we want to measure for our standard oscillation analysis. But they don't just tell us all the mixing angles and delta CP, but also possible BSM. So meaning that I'm still going to measure, let's say, what are the survival probability of muon neutrino go to muon neutrino as a function of E, measuring muon electron appearance probability as a function of E. But they tell us a whole lot. Okay, and I think I'm going to use a concrete example. That's called short baseline anomaly. And specifically, I sort of already hinted at that it's possible, the solution is a possible 1 eV star neutrino. I'll just explain what this is. Okay, this was really a case that I think was driven by the experimental anomaly. So about, let's say, 20 years ago, an experiment called LSND trying to measure neutrino oscillation. And what they had wanted to measure, one of the channels they look at is they produce new mu bar. And this is from pion decay at rest. Okay, so they have some new mu bar source, that's fine. And they want to measure how much of that have turned into new E bar after some oscillation distance. And right now, based on our current understanding of all the mixing angles and delta M squared, as we know, we mostly have measured them. Right? Most of the values we know up to like a few % precision. So using our standard framework, we can predict what this oscillation probably should be. And it should be 0 because they're not basically set up at the correct baseline and stuff. But instead, what they had measured is some non-zero probability. And you can always, when you see a non-zero probability, so meaning that in their experiment, they didn't expect to see any new E interaction, but they have seen them after some background rejection and all those things. And okay, so then the first thing you think, since you're measuring oscillation and there's some additional neutrino electrons that you think, electron neutrinos, so they try to fit this using our just standard 2-flavor vacuum oscillation appearance probability that we've seen a few times. And this gave them a decent fit. So meaning that because this is not by standard oscillation, so you cannot, standard we have 1, 2, 3. So the mixing mass is 3, 2, 1, 2, 1, 3, 1, and 3, 2. So none of those fits. Instead, they have to fit with a different mass square. That's about 1 eV squared. And also, they get a different mixing angle. And mixing angle, I'm just going to write this sine square. It has a range, but let's say it's something like 0.01. And with this, they got a pretty good fit. Okay, so which is why this additional stereo, if exists, is considered at 1 eV, because this would be the mass square difference between M4 square minus M1 square. And we know that all the active neutrinos are much, much lighter than 1 eV, which means the mass square difference should be close to the actual mass eigenstate, which is about 1 eV squared. Okay, so this obviously was a big deal. If this signal were true, then we would have discovered a fourth neutrino. So the first guess is, would this neutrino be active? Let's say it doesn't have to be sterile. We know that standard model has 3 families, E, mu, tau. There could be a fourth one. That cannot be the case based on existing experimental measurements. Anyone know any measurements that would obviously rule that out as a active neutrino? Yeah. Yeah, ZDK. Because we know the invisible width of ZDK, we know that this cannot couple to Z. Which is why that, for instance, we know neutrinos has mass. So we could have a term that simplest thing to do is a Dirac mass. And this would be something that not coupled to Z, so not charged, in standard model, and still oscillate to neutrinos, hence the name stereo neutrinos. And some of you might hear, stereo neutrinos, it's kind of like, I guess it's a little, okay, so in spirit, the parameter space for stereo neutrinos is kind of like dark matter. So there's, order of magnitude in terms of the possible mass, and coupling depends on what you want the stereo neutrino to accomplish. So, for instance, if you think about neutrino mass model, which I will not have time to talk about, maybe you're more familiar with very, very, very high stereo neutrino. If you're more thinking about stereo neutrino as a kind of dark matter, for instance, then you're maybe more familiar with like KeV stereo neutrino. And so I think this one, I just want to explain the mass range. As far as I can tell, this is really motivated by this experimental signal that points to a 1 eV possible stereo neutrino with such mixing angles.
What are these letters, LHN?
Lepton, Higgs, and the right-handed.
It's in Lagrangian.
Yes.
Oh, I see, sorry.
Yes. Yes. Yes, I don't. My best curly effort. Okay, so then this came up, and this was pretty well fit by a fourth neutrino. So then the simplest way to explain this is, earlier we said we have E, mu, tau, and we have a 3 by 3 mixing matrix, and we have 1, 2, 3. This is our standard oscillation picture, right? So then the simplest way to fit this picture is that if I have a fourth state, and I'm going to call the flavor one stereo, and fourth mass eigenstate, which means I now have a additional row and column of these things. So now it's a 4x4 mixing. Now you might ask, why is it 4x4? Because initially I have 3x3, and I could obviously have more. That is certainly the case. And this is basically the simplest way we can accommodate that signal. So this has been tested the most. So this is what I'll focus on. So this is typically called, like 3 plus 1. As I will explain later, for instance, then there might be some tension here. People have also tried to examine 3 plus 2, because we go from the simplest addition. Question?
So if it's not charged on the standard model, why does it mix with the other?
Well, okay, so then, for instance, the simplest way to think about it is the one I'm familiar with is really to consider, something like this. So then you would diagonalize the mass matrix with all the neutrinos, and then give the
Not charged means it's a singlet under the gauge group and doesn't couple to the vector bosons, but it could still have this kind of coupling to standard model particles.
Right. Yeah. You are exactly correct. If we have, this is 3 plus 1, but obviously we could have more. If we have any of these additional stereo-neutrinos, which again, because neutrinos have mass, we more or less think that's the case. This means the 3 by 3 that we're testing right now should be non-unitary. And of course, how non-unitary, okay, so obviously right now, most of our data sort of fit except for this signal that we'll talk about, which means it's the 3 by 3 PM-NS matrix is probably mostly unitary. But we would expect some mild amount of non-unitarity in this 3 by 3 mixing. And this is also, so there's essentially two ways to test the existence of a stereo-neutrino. Essentially, first, if it's very light, like in this case, it can directly participate in the oscillation, which we will discuss how we test them. Or let's say, even if the stereo end up being very heavy, so that we cannot directly produce them through pion decay, then that's totally right. So the way we would test it is to test whether this PNS matrix is unitary or not. Yeah.
When people did this did they try to fit two stereo-neutrinos just to see what masses you could get?
Yes, the question is, did people fit 2 stereo-neutrinos? I'll comment on that in a second. Okay, so then the simplest, again, explanation for L-D anomaly, which was a while ago, was 3, people typically call it 3 plus 1. So let's examine the possibility. How would we examine this if that's the full picture? And okay, again, just to be explicit, the assumption is now the 4 by 4 matrix is strictly unitary. There's no additional stereo states. Okay. So then this was an experiment, and this was a very challenging experiment looking for a small signal. How do you know it's a small signal? Because oscillation amplitude is controlled by sine square. So the sine square, again, has a range, but let's imagine it's something like 0.01, which means you're looking for a signal that's like 1%, right? 1% measurement is difficult. So then people built a different experiment later. That's called mini-boon. And trying to examine this. And again, because you want to test oscillation, you want to try different settings so that experiments have different systematics. And if you want to test the same signal, the only thing you need to control is you can change L, you can change E, as long as your L over E is, as long as your delta M square for 1, L over E is something like order 1, right? So this is what mini-boon did. They use a different neutrino source. They use an accelerated neutrino source, which have a different E from L/D, which also you adjust your baseline so that you're still sensitive to this 1 eV square mass difference. So they did this, and they also measured 2 channels. So both in the neutrino mode, nu mu go to nu E, and the anti-neutrino mode, nu mu bar go to nu E bar. And so if it's a standard model case, if it's a standard 3 by 3, we should not expect appearance. And they look at both channels, and they found excess. Okay, so this is awesome, right? We saw some experimental hints, and we're not sure, so we built a different experiment in a very different systematics, different detector technology, trying to see this. Okay, so now have we discovered 1 eV star neutrino? Oh, and I also forgot to say that for mini boom, because they discovered a axis, you can also plot your parameter space in terms of theta, in terms of sine theta square and delta m square, right? And it's like, it has overlap with the LS and D parameter space. Both are pretty large regions, but they have overlap. So that seems excellent. Well, but it doesn't quite stop there, because if our whole mixing is 4x4 matrix, and I find some crucial mixing parameters there, that means I can write the following. My appearance probability, where we see the axis, can write that as, so the mixing angle that I wrote there, if I express that in terms of matrix element, is U mu4 square U E4 square and sine something L over E term, which I would not, that's not a key, so I will not write that. Okay, but this means, so if this is non-zero, if this is something like 0.01, which means this is not zero, this element, mu4, and E4, so both are non-zero. But the power of oscillation is, of course, you can predict other channels. So given this, I can see what happens if I measure disappearance channel as a cross-check. Right? So you can write this as 1 minus 4 U mu4 square 1 minus U mu4 square. And this L over E thing here. And then they're identical, so I'll not write them. Okay, which means if the U4 is now 0, then this is now 0. So I should see some disappearance signal in the mu channel. Similarly, I can also produce an electron neutrino beam. I can measure how much of them have disappeared. And this oscillation probability looks very similar to this, just replace mu to E. Yeah. So this means that this provides a very powerful consistency check if I truly believe in my so-called 3+1 model, that I see an appearance channel, I should see some weird disappearance signal in both nu mu and nu E channel. And if everything checks out, then I can confirm that I have indeed discovered a 1 eV star neutrino. And unfortunately, we have carried out all of these measurements. So we may have seen something here. So I'm going to say, initially, we thought we saw a disappearance signal. But then later, people check systematics and become unsure. So I'm going to label it as that. But the muon one, we're pretty sure that we have not seen a additional disappearance signal. Yeah.
Sorry, what do you mean by disappearance and appearance?
Sorry, so if I start from, it's just a common terminology. So if I start from some flavor, go to a different flavor, I call that appearance. If I start from a flavor and measure how much have survived, this is called yeah.
What was the statistical significance of the excesses in mini?
Great question. What is the significance of these axes? So that's very high. The last time Mini Boom put out release, I don't remember the exact number, but it's something around 5 sigma. I think it's more than 5 sigma.
Right. So you'd call that a discovery, you just don't know exactly what you've discovered, right?
Right, so the question is that a discovery or, okay. So the question is,
Sure, I just happened to be looking at the Wikipedia page for
oh,
Mini Boon.
thank you.
It's in 2018. It said 4.8 sigma Mini Boon alone.
Yeah.
6.1 sigma when combined with LSND.
Okay, so 4.8 or 6.1. Okay, so let me comment on that. I think there was another question. Yeah. So it's a separate question. I will answer that because I know the answer. So the question is, how tight is the constraint on 3x3 unitarity? And it's not a single number because there's a bunch of conditions, but it's something like the worst, which is like tau related, is something like 20%. The best, which is E related, because we measure E really well, is something like few percent, if I remember. Okay, question?
Yeah. Do these consistency checks assume unitarity of the 4x4?
Correct. Right. So important thing is these things that I write down is strictly assuming that it's just 4x4. So I will comment on that with the earlier question of like 3 plus 2. So is it 5x5? So now come back to your question about this is extremely high significance, of course. So what could it be the case? This is something, again, people have, this is like a 20-year anomaly, so people have argued about this in a very long time. So what's the many possible explanations, but one, for instance, you don't see neutrinos in your detector, right? You never see them directly. Whenever you say you measure the nu E axis, it's always like, did you really measure nu E or did you measure something else? And that's a very hard question. Again, remember the significance is high, so I think people, and if you've seen their publication, the axis looks very large. But remember, this is something like a 1% axis, so there's a lot of background there. So if you see, so one thing, for instance, in Mini Boon that people argue a lot is that if you think you see a nu E, which means you have nu E interacting something and give you an electron and plus something else. So then you see this electron, but it's pretty energetic. These are like sort of, let's say, GeV scale electron. What it could be, one thing that people questioned is nu E plus something can produce, let's say, just a pi zero, because you produce a lot of pions. This pi zero and plus something else. And this pi zero could decay to 2 gammas. And the detector technology, and let's say maybe you missed maybe 1 gamma fall below threshold or something, so you could be left with 1 gamma. And the detector is such that this electron, this gamma, electron gamma look pretty similar in detectors typically because they both do an electromagnetic shower. So one thing that people argued a lot is like, do you really know your pi zero production? And of course, and the experiment argued that they have examined all the systematics, and this is not pi zero, but some people keep saying maybe it's pi zero. So there's background like this that, it's still being debated. Which is why this signal, okay, so the conclusion is this is still an open debate. People still fight over all of these things, what is the measurement? So for this generation, the short baseline program at Fermilab will test the signal. And there, it will be super conclusive when all the detectors are online for the following reason. So first, you're seeing an oscillation. So ideally, you want to see how things actually oscillate, like a sine function. So then the short baseline program is, so let's start from a neutrino beam. And this will be, let's say, nu mu or nu mu bar. And they will have a detector that's very close to the source. So SBN near detector. I'm going to write it like that. And then some distance away, they will have a middle detector, microboom. And then they'll have a further away detector, egress. Obviously not to scale, but the point is they cover a pretty large L distance, range. So that hopefully you will see how the signal, if it is indeed an oscillation, you will really see how things change as a function of L. Now another thing, again, people fight really like for the mini boon is, are you measuring nu E or are you measuring photon? Because this is, in this detector, you cannot tell electron and gamma apart. But electron gamma can be distinguished in liquid argon detectors. So, and all of them will be using liquid argon detectors. The full name is liquid argon time projection chamber. The idea is really that you can see particle tracks. So if you have an electron at a vertex, you will see this is a vertex. I'll see electron, and it's going to produce gamma. It's going to, let's say, produce gamma and more electrons, and you can see a shower like this. What would a gamma look like? You have an interaction vertex, which has a bunch of activity. And gamma would propagate a lot of a distance, leaving no track, because it's not charged. Then you'll start knock on a hard electron, and it's going to start a shower. So they will look different in the detector as one has a track that's attached to the vertex. One has no track. There's a little gap to the vertex. And the experimental design is such that you should be able to tell this apart. So this is possible, even if we cannot figure out how much pi 0 is produced, experiments can tell them apart. So this should be, figured out. And lastly, I think the question on 3+2. So 1 second, let me answer this question. So these formula are only correct if we assume it's strictly 4x4 mixing. And we test that because initially it fit the data very well, and it's a simplistic test. When this becomes some tension between, people call it like appearance and disappearance, just basically because these formula don't all fit, then people extend it, start testing 3+2. So meaning that assuming the whole thing, I will have additional row, so it's a unitary 5x5 mixing, which of course bring in more parameters. And that's also complicated because although you have not so tight relation, but there's still some relation you can test. And initially it looked better, but then later on it also seemed to have some tension between the data set. So I think at this point, the picture is just really unclear. And the good news is that the status of these threat detectors, I think microboon's running, Icarus is, I think, being installed or something like that. So hopefully this is something that we'll have super definitive answer just in a few years. Yeah, 1 second.
Yeah, this one microboon is already running, and for now it seems to me that they don't find the excess that needed to have. So is it not enough to convince people that they, because I thought the experiments were quite similar. So.
Great question. So microboon has been running for a few years and has put out their analysis. I think the first analysis on the low energy axis, that's what they call it. And basically that generated a lot of debate because I think what happens is the first paper that got press release sort of gave the impression that they had completely killed off this region, the mini-boon axis region. And that's not quite a fair representation. Essentially what happened is they were testing it's a little hard to say accurately, but spiritually, imagine it's like this. They basically test the best fit point of the mini-boon axis in some way and seem to have exclude that. But then the argument is you can't really just test a single point, right? The parameter, the region is pretty large. So I think they have not tested the whole region, not in a way that convinces everyone. Yeah. And there was a question. Right. Right, so the question is essentially what about other experiments? Because this is obviously a very intriguing signal, so I think pretty much every oscillation experiment, conducts such a measurement. And what I can say is, I feel like it's a very complicated situation, as in, if everyone else had agreed that this has been excluded, then I think probably people would be convinced. But for instance, like one thing, you're using pretty much these summarize the situation, like the EE channel. So do we see something weird there or not? And that's the thing that initially we thought that we had seen a additional like EE disappearance, which would corroborate the story. Right, then people are like, well, yeah, but they missed some calculations and some things were wrong. So it's just all of these measurements have their own sort of systematics, and then people really fight about it. So my personal feeling is, once all the short baseline experiments, short baseline program come online and test this, hopefully by then people will be fully convinced one way or another. But I think at this point, right now, I think if you poll different people, I think you will not get everyone will not agree on some answer. Yeah.
So for the mixing matrix, can you imagine a non-square matrix, like a 3 by 4?
Right. If I remember, you don't. So you might treat that as okay.
Repeat the question, Shirley.
Sorry. The question is, the mixing matrix, does it have to be square? Can you do it 3 by 4? So I think it's the following. If we consider all the, let's say, stereo neutrinos, we don't know how many there are. If you consider full stereo neutrinos, you would, regardless of their mass, you would definitely get a square matrix because it's coming from diagonalizing the mass matrix, right? So in that case, I cannot think of a scenario where it's not square. But realistically, when we do measurements, like when we try to fit stuff, we're actually not really using the square information. For instance, just look at this example. The thing that really makes, because we're going from, the way to read it, you're going from mu to E. So the fact that I have nu S that has additional rho does nothing. The only thing that matters, you can see, you go from U to E, you use all nu 1, 2, 3, 4. So in fact, the only thing that enters this calculation is a 3-row, 4-column matrix, practically, for oscillation calculation. But the whole matrix, I think, has to be square.
I'm sorry, I'm still confused about this. Is there a theoretical reason that for bit, let's say I only have 3 flavor bases, but I have 4 mass bases?
Well, I guess in some sense, okay, so then that depends on what you mean by nu S, right? Because nu S doesn't couple to, it doesn't couple to.
No, I get rid of nu S. I only have 3 on this.
Yeah, that's what I'm saying. I think that's fine.
I think the reason this is impossible is because the flavor and mass spaces, they're not separate spaces, they're the same space, so they have to have the same dimension. And this is just a rotation from like one set of coordinates to another. You can't do a coordinate shift that changes the dimensionality if you're in the same space.
Yeah, I agree. And so then when you actually compute stuff, it doesn't matter what I call nu S1 or nu S2 because they don't participate in anything. So realistically, when you do calculation, that row doesn't matter. But the whole thing should be matrix, should be unitary, so I guess it has to be related to the column.
Non-square matrix can be unitary.
Well, so the whole thing has to be square. Yeah. It's just like.
It's not a copy or something like that. You can have square, but here you just diagonalize the matrix, so you
Okay, maybe we can talk more after. And so then that pretty much wraps up the discussion I plan to have on short baseline anomaly. Any other questions on the status of this 1EV? Okay, if not, then let me make a quick remark that I will not write down the example of. So it's using oscillation to probe stereo neutrino is kind of like obvious case, right? Because it oscillates just like an active neutrino, so obviously we can test this. So that's fine. But oscillation actually can test more. So for instance, and again, I'll just explain this conceptually. Remember that for something for Dune, one of the amazing thing is that it will actually be sensitive to matter effect. And matter effect really just coming from understanding how neutrino and electrons scatter in this case, or matter scatter. Which means that you can alternatively think about matter effect as some sort of probe of neutrino matter interaction, right? Because that's the thing that contributes to matter effect. So this means that it's not just neutrino oscillation vacuum. If you have some, let's say non-standard neutrino interaction with matter, or for instance, other scenario people have considered is, let's say neutrino could have, suppose we have ultralight dark matter, and neutrino could couple to the ultralight dark matter. So these would all induce some weird signature on neutrino oscillation. It's not gonna be a signature that looks like a sine square, L over E. But if we fully examine how the oscillation signal will look as a baseline and energy dependence, then these things will show up. For instance, if you think about the ultralight dark matter, the interesting signal that people come up with is the oscillation probability would change as a function of time. So we conduct these experiments over 10 years, then maybe the oscillation in the first year and the last year would be different. So people look at all different kinds of signals to look for, essentially I summarize them as, because neutrinos actually experience interaction on their way of propagation, and these experiments are sensitive to that. So it probes a variety of sort of exotic interactions. Good.
Got about 10 minutes.
Yes, thank you. Okay, so then I'll summarize another kind of very popular, I think, use of these experiments. And it really has nothing to do with neutrino at all. So say it's basically treating these experiments as beam dumps. Okay, so here's a general idea. So let's focus on the near detector part and see what happens. So I have a neutrino beam. And let's be a little more careful about how the neutrino beam is produced. So they're produced by the following. I have a very energetic proton beam. So for instance, I do need something like 120 GeV proton beam. And it's hitting a target, as in solid. And so proton target collision will produce a bunch of pions, right? So all sort of charged in the 0 pions. And then when we want the neutrinos, what happens? This pion would decay. Let's say this pion would decay here, and give you a neutrino, and these neutrinos would interact in near detector, like this, which is very big. And then they'll go on to probably far detector, but let's ignore that. So this is what happens from beam to near detector part. Now, if you look at this, and if you just don't care about these neutrinos, but rather you care about, let's say, variety of light degrees of freedom, exotic degrees of freedom. So here, for instance, popular scenario people look at would be light dark matter. Axions. Or specifically, let's look at dark photon. So things that couple to standard model with some portal. And when I say light, I'm talking about, let's say, less than 1 GeV. So if any of these exist, and sort of like in this light mass range. And look at the scenario. They'll be produced abundantly. So for instance, ow. Okay. That was painful. So let's say if I'm looking at dark photon, so the coupling term that I'm looking at with a mass of, let's say, anything below GeV or so, that kinetically mix with my normal photon. Suppose this exists. What would happen? Well, many places where this can be produced. First, when a proton collide in my target, what could happen is proton could Bremsstrahlung a dark photon. Instead of Bremsstrahlung a normal photon, it could Bremsstrahlung a dark photon, right? Or let's say I produce a pi zero, which pi zero decay to 2 photons. But it doesn't have to decay to 2 photons. It could decay to a photon and a dark photon. And plenty, because there's protons, a bunch of mesons is around, so plenty of production channels. So I'm just listing like a couple. And then let's imagine you have produced a dark photon around the target region, or around target region. What would happen? Well, it's not charged. Yeah.
Should there be another A prime with the lower mass?
Yes, this is a square. This is just master. Okay, so then this dark photon is not charged, so it's just follow essentially the same trajectory as neutrinos, and it's going to arrive at your near detector. And once they arrive at near detector, how would you search for it? Now, remember that near detector is a super precise tracking, low threshold, giant detector. So then you could look for instance, dark photon could decay in near detector. And this will look very different from a typical neutrino standard model interaction, which will be, in this case, a background. Okay, so this is a very simple picture of the strategy people use to search for these things. And if you are familiar, with beam dump or fixed target kind of experiment, I mean, just looking at the top figure, that's essentially exactly the same as a fixed target or beam dump experiment. And so from that perspective, the design is essentially there's no difference. And the only thing extra is there's a bunch of neutrino standard model interaction that you have to consider. And so I do have time to write this down. So if you think about experimental sensitivities, there's a couple of things to consider. For instance, what is your beam power? So how much proton is colliding on your target? Essentially, imagine it's some sort of flux. So for instance, Dune has 10 to the 22 POT. Compared to, let's say, typical beam dump kind of experiment people look at, so I will just copy like NA64 as the example. So it's 10 to the 18. Or some other experiment you might hear, for instance, phasor would have something like 10 to the 17, and SHIP will have something like 10 to the 20. So Dune actually has higher POT than any of these experiments. For all of these experiments, one key parameter that you might not think about is the decay length. Another way to say it is it's how far away the detector is from the production point. Because the idea is the following. So it wants basically the decay channel is a more clean channel to search, so you want things to decay in your detector, which means you don't want you want the coupling to be not so big. If the coupling is too big, then things will decay right away, and it will not reach your detector. At the same time, if the coupling is too small, then it will still be stable at the decay, meaning that it has not decayed, so then you wouldn't have a signal. So basically, the decay length sort of controls which is your epsilon, or which is your coupling ridge you can search for. And here, Dune is just quite complementary to other experiments. So for instance, Dune is about 500 meters, so from the production to the near detector, whereas something like Na64 is at about 100 meters. And various experiments go from basically 50 meter to 500 meter. So the idea is that it has a different decay length so that it probes slightly different part of the parameter space. And something else that's important is like, for instance, the experimental threshold. Because, obviously lower threshold, the better it is to identify signal. And Dune has something like 10 MeV. And I think Na64 has something, okay, I didn't copy this down, has something like tens of GeV. Yes. So essentially, this is really, like I say, doesn't really have much to do with neutrinos at all, but just because essentially the high beam intensity and the big detector has low threshold. So it's actually quite complementary as a beam dump kind of setup. And you can use the setup to look for light particles. Okay, so I'm running out of time. If you want to learn about supernova neutrinos, come talk to me afterwards. Okay, so to summarize what I talk about, so hopefully I give an overview of standard neutrino oscillation scenario, and the key takeaway is for the 3x3 mixing, we sort of, at least we know how to compute things, and we have measured all the mixing angles and all the value of delta M square. And the next generation experiments will really have robust sensitivity for delta CP phase and mass hierarchy. But at the same time, even for something like oscillation that people have done for decades, there are still interesting open questions. And for these experiments to successfully run, we definitely need to figure out better ways to compute these cross sections. Again, plenty of open questions there. I mean, there's more open questions than there are answers. And there's a lot of things you can do with these experiments, and I wish I had a little more time to talk about them. So you can measure oscillation to depth, and it actually probe a variety of new physics scenarios. Or you can just dump the far detector and just use the near detector to probe a bunch of things. Or you can also measure things that has nothing to do with the neutrino source. So for instance, the far detector is just giant. And there's a bunch of astrophysical things that you can possibly measure. And there are